Yesterday that was, what was it, 8.5? You got to see the reaction. Some of them were fantastic. We did save good ones for today, though. But this balancing takes practice. And there were help videos for many of them if you got stuck. A lot of these were not very difficult to balance. How did we know? They tell you what the products were in this first one. Did they tell you the products? No. How would you know what the products were? They told you it was a decomposition reaction. Decomposition reaction means that the compound, decomposition, we start with one compound and it breaks apart. That compound breaks apart. Well, this is not a hard one to break apart. We only have silver and we have oxygen. That's all we have. Silver and oxygen. If there were more elements in there, then it would be a little more difficult to figure out what the products were. But a decomposition, this thing has to break apart. And we'll see in some later reactions that you can't always tell what the products are unless you do some additional tests. This is thermal decomposition, meaning we added heat. Why do I have a 2 after the O here? There's no 2 after the O here. Why is there a 2 after the O here? Yes. The 2 after here is saying that there's one molecule of oxygen here. There's one molecule of oxygen here because there's no number written right there. There's one molecule. The number of molecules is in front. This is the number of atoms on the molecule. So an oxygen molecule has 2 atoms. Why? Do you remember Brinkelhoff? Oxygen is one of the diatomic elements. Each oxygen starts with 6. They need 8. So the 2 oxygens join up, share 2 pairs, a double bond to get their 8. So it's diatomic because oxygen can bond with another oxygen atom to satisfy the octet rule, becoming stable. So you have to put the 2 there. Anytime oxygen's by itself, there's a 2. But there's no 2 here. I thought oxygen was diatomic. Remember, when we have something like this, the subscripts come from balancing the charges. Silver's always 1 plus, oxygen's 2 minus, so we crisscross. The 1 from the silver came down here, the 2 from the oxygen came down here. The only time oxygen must have a 2 after it is when it's by itself. The subscripts, when oxygen is with other stuff, depend on what it's balancing with. So with the 2 here, we need a 2 in front. 2 times 2, that gives us 4 silvers. Question on that first one. Another decomposition reaction. On this one right here, on this decomposition reaction, it is also a thermal decomposition, meaning we have to add heat energy. But on this one, we're starting with lead 2 nitrate. Lead 2 nitrate. What it decomposes into, we don't really know for sure. They did do something, if you remember, they did do something to show that oxygen was one products. And that they showed with an incense stick. They had that little burning stick, pretty much blew the flame out, inserted it into the reaction, and it burst back into flames. Oxygen, when oxygen is around, it certainly helps things to burn. It is one of the products of combustion. How do we go about balancing one like this? Where did all these numbers come from? Well, if we count the oxygens on this side before we balance it, we have a 2 and a 2 is 4 before we balance it, and 5. Well, here we have 3 here with a 2 outside of it. So that means we have 2 NO3s in this compound. 2 NO3s would give us 6 oxygens. That 2 means I have 1 NO3, I have another NO3, 3 and 3 is 6. 2 times 3 is 6. So we have 6 oxygens. Here I have how many nitrogens? The 2 goes with both of them. So how many nitrogens is that? Ignore that 2 in front right now. That would be 2, yes? So we know that we would need at least a 2 right here. We know we would need at least a 2 right there. That's the minimum. When we go to continue balancing, we're going to see something rather interesting here. If we have 6 oxygens right here, we put a 2 in front of this, that's going to be even, that's going to be even. I have to put a number in front of that. Why? Regardless of what number I put here, anything times 2 is going to be what? Even or odd? Anything times 2 is even. There's a 2 here. Regardless of what number I put there, anything times 2 is even. Even and even. We already showed you that we have to have an even number of oxygens here. Are you following me? That means I need an even number in front of here. So I have to put the 2 there. Now we can get rolling. I've got this 2 here by realizing that I have to have an even number of oxygens, yes? If I put a 2 there, I must put a 2 there to give me 2 leads. 2 nitrogens times 2 is how many? Are you understanding how to balance this here? We know we need this 2 here. I already have 2 times the 1 nitrogen is 2 times another 2 is what? 4. So I have to put a 4 there. Now the numbers are starting to fall in place. The leads are balanced. The nitrogens are balanced. Now I can balance the oxygens. 2 times 3 is, times 2 is 12. Here's 2 O's. 4 times 2, there's 8 O's. 2 times 1, there's 2 O's. That's 12 O's, people. That's 12 oxygens. We are balanced. This was just done trial and error, looking at the numbers, and especially looking at odds and evens regarding the oxygens. Do we have any questions on number 3 here? This one, not difficult to balance. It's already balanced. Red litmus paper, as we learned in the acid-base chapter. Red litmus paper turns blue in the presence of a base. In that experiment, in that demonstration, the demonstrator or experimenter put the litmus paper in, it turned blue. The hydroxide ion is the strongest base we can have in solution. The hydroxide ion is OH minus. Bases attract the hydrogen ion. So the hydroxide ion is very good at attracting the hydrogen ion. Question on that one? Anything on number 4 at all? Was there anything on number 4 at all? Take a look at this. Question on anything regarding number 4? We're coming into some of our favorite demonstrations. Number 5 were some beautiful. This is the one where they had that camera up close and kind of slow motion, the precipitation reactions. That was fun to watch, that one. Do you remember how pretty it was? Saw those swirling colors of precipitation forming in the solutions. It was very soothing to the eye. Questions on any of these? Practice is balancing, practice balancing. These are fun problems to do. Balancing is a fun mental challenge. Now, some of these are very easy. They're not mental challenges very much. Some of the other ones, though, were slightly more of a challenge. The propane experiment, wasn't that the cool one? Do you remember watching that one? He had the coiled tube, filled the coiled tube with carbon dioxide and water vapor. Do you remember that? And then he turned on the propane, and he lit the propane, and the flame went spiraling back through the tube. Do you remember that demonstration? It was fantastic. What an awesome demonstration. But they were burning propane in a combustion reaction. Did you get this one okay? Did everyone balance this one okay? There was no help video for this, was there? On purpose. Why? Combustion reactions are very easy to balance using the what rule? Who remembers the easy rule for combustion reactions? Yes. The Hollister rule is indeed correct. That is where we balance them according to the Hollister acronym. Hollister Company. Hydrogen first, carbon second, oxygen third. That is the order we balance them, and then we remember that we need an even number in front of the water. We need an even number right there. Hollister rule. So we do hydrogens first. We have 8 hydrogens on this side. So there's 2 here. So I need to put a 4 in front. 4 times 2 is 8. 4 is even. So this part of the Hollister rule is finished. We don't have to worry about it. Hydrogen's balanced. I have 3 carbons there, so I put a 3 in front. You're like, wait a minute, 3 is odd. No. The only place we need an even number is right there. Because we have to have an even number of oxygens overall. Because there's a 2 here. We can never have an odd number of oxygens on that side. So carbon is now balanced. Now I do oxygen. 3 times 2 is 6. 4 times 1 is 4. 4 and 6 is 10. 5 in front, we're done. The products of a combustion reaction. There is one like this on the exam. If you remember the Hollister rule, it's seconds to balance. But they do not tell you what the products are. You have to know the products of a combustion reaction are CO2 and H2O. And that comes into play on this very reaction. When you are asked to explain why they filled the tube, in this one you were asked, why did they fill the tube with carbon dioxide and water vapor in that demonstration? It was a fabulous demonstration. If you didn't get a chance to watch it, watch it. Why was the tube filled with carbon dioxide and water vapor? Can carbon dioxide be used to put out a flame? Yes. Does water help smother flames and burning? Yes. So they filled the tube with stuff that keeps things from burning. Then they put propane in the tube and lit it. Before they lit it, propane was put in the tube. So propane was in the tube with carbon dioxide and water. So here's our tube. I draw this for you on this board. Here's the tube. Here's an opening on the tube. They filled the tube from this end right here with carbon dioxide, water vapor, and propane. This tube was left open right here, right on this end. What is in here? Propane, carbon dioxide, and water. There was not oxygen in there. The only place oxygen was right here on the outside. So when they opened this end of the tube, oxygen could go in. Then they lit it. They lit it. Fire! They lit it. You need oxygen to burn. Yes? The only place oxygen was right here. So the flame moved into here. But oxygen followed the flame. There was no oxygen in here on that part of the tube. If that tube was completely filled with oxygen and propane when they lit it, what would have happened? Would it have been a slow traveling up that tube? No, it would have went and ignited right away. So only the propane, as the oxygen started moving in this way, that propane could then combust. It was a brilliant demonstration. It was a brilliant demonstration of the combustion of propane. When you put the products in the reaction, it can slow the reaction. Even cease the reaction when you put the products in there. How about this reaction right here? Was there any trouble on this one? Number what? 7. Any difficulty on number 7? Any trouble on the balancing of number 7? Remember, there is balancing help on that. What about balancing the next ones? The next ones were the challenging ones to balance. If you balance the next ones, and if you haven't done your homework yet, I would not even look up and look at the answer. Because the best way to learn to do these is on your own. So if you haven't tried the next ones, look away. If you did try the next ones, this was the fantastic explanation of what catalysts are, how catalysts work. But here are the two reactions that we looked at: the chemical volcano and the fire blizzard with chromium oxide. Two well-known demonstrations. Balancing this one and this one right here. This one was especially challenging. Questions on any of this? This is a nice indication. This thing was really good for explaining how many catalysts work. Take a look at this for a second. On this reaction right here, there was an explanation of how the catalyst, in this case, they were using potassium iodide for this reaction right here. If you want to know how catalysts work, the role of the catalyst right here, take the time to read that. Because a lot of people are not sure what catalysts actually do. They help reactions, but they themselves are not consumed in the reaction. They help them to occur. How about here? How about why this not be considered a single? Why is this not like a single displacement? Why is this not really a double displacement in the purest sense? Question on that. Yes.
I have a question on the one above. So
Here?
yes. So the first one there's 4 nitrogens, but in the other one
There's 4 nitrogens where?
uh,
Here?
yes.
No, there's only 2 nitrogens. This 2 means we have this. NH4 and another NH4. So how many N's is that? 2. How many H's are there? The subscript to nitrogen's 1. 2 times 1 is 2. 2 times 4 is 8. Yes? Good question. These were like fun puzzles to solve. Balancing is a puzzle-solving thing. Questions on these, though? Do you see why they can't be considered, in a pure sense, a single or a double? This one right here. It's compound, element, compound, compound. A single is compound, element, compound, element. A double's compound, 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 compound. So this is really oxidation reduction. How do we know oxidation reduction? Oxidation reduction reactions, their charges are essentially changing, or their assigned charges. An element by itself is always what? Element by itself always has an oxidation number of what? 0. Or there'd be a charge written there. Oxygen here is going to be -2. Oxygen here is also -2. That makes this nitrogen +2. Nitrogen right here is what? -3. Hydrogen is +1. So nitrogen goes from -3 to +2. The hydrogens continue to be +1. Yes. If you go from -3 down to +2, I'm sorry, if you go from -3 up to +2, your number increased. You're said to be what? You're said to be oxidized. Yes? Oxygen goes from 0 down to -2. Oxygen's number was lowered or reduced. Why do you suppose they say nitrogen's been oxidized? What did it join with? Now you understand where the term oxygen oxidized comes from. When they first started studying reactions, it seemed like when oxygen joined something, it caused the thing it joins number to go up, because oxygen's notorious at being able to hog electrons. Oxygen's number was lowered, it was reduced. Fantastic. So much chemistry yesterday if you took the time to do this assignment. Notice we had examples of each of the types of reactions. Look. This could be called double displacement, couldn't it? Some people could call this double displacement. It really is double displacement, but it's a special category all onto itself. It's a special category all to itself. Why could it be double? Double, the first thing here joins with the second thing here. In a double, first thing here joins with the second thing there. They did. The Na joined with the SO4. The H joined with the OH. The H joined with the OH. That's what water is. An H that broke off an acid and joined with the hydroxide ion. HOH is water. I always used to call water, until my teacher made me stop, hydrogen hydroxide. That's really what it is. The hydrogen ion joining the hydroxide. And they're like, no, it's water. I'm like, well, could I at least call it dihydrogen monoxide? No, it's water, dog. Come on. Why y'all gonna play like that? You see why we could call that double? But it's a special case of double. It's an acid-base neutralization reaction. This is one of the 6 strongest acids known to mankind, sulfuric acid. OH is a base. When you see OH in a formula, you've got to think base. There's my base. There's my acid. What does an acid-base reaction always make? Water and what? Water and what? Acid-base reactions always make, thank you, water and a salt. They make salt water. Salts are a metal such as sodium, and in this case, my nonmetal is the sulfate ion, SO4 2-. Folks, I could not think of a more exciting way to get into balancing reactions than to give you an opportunity to watch with your own eyes demonstrations of the reactions you were balancing. It was thrilling. Honestly, it was breathtaking. Like, you're watching these reactions and you're like, oh my gosh, how fantastic are these reactions we are watching? They were marvelous. Captivating. Today, you're going to get to see some additional chemical reactions, some of my favorites. Today, you'll have the opportunity to watch and then balance. Today, they are not going to tell you what the reaction type is right away. I want you to look at the reaction and classify it. Is it single? Is it double? Is it synthesis? Is it decomp? Is it acid-base? Is it combustion? Is it oxidation reduction reaction? We looked at 7 types of reactions. You'll classify the reaction and balance. Try to balance it. Try to classify it and balance it before you watch the demonstration. Because you want to practice the balancing. Very often in the demos that you're watching, they will show you the balanced reaction. Learn to do it on your own. Do you like solving those? What are those little puzzles called where you got like boxes and numbers and you fill out the numbers and you have to have them add up to certain things and all that? Those are like Sudoku puzzles, aren't they? Who? Spadanko puzzles or something like that. Those puzzles where you write the numbers on, that's kind of like balancing. I remember when we used to go on family trips as a child. I remember my dad would keep us entertained for hours on end. He would have a bunch of reactions on little strips of paper. And he would throw the strips of paper into the back. I'm in the back seat with my brothers. He would throw the chemical reactions for us to practice balancing in the back. The fights would begin because we would try to grab up as many as we could. Punches are being thrown, headlocks, trying to rip them out. Nothing worse than having a paper in your hand where you get a chance to balance it and your bigger brother rips it out of your hand, giving you a what? What's that called? Like where you're trying to hold paper and it like gets pulled out of your hand. That's it's like a paper cut, but it like if you're not careful, look what it could do. I remember holding one right here and like I had my hands on it. My brother ripped it off. It severed my finger. Did my dad stop? No, they don't stop the car on the way to vacation. They don't stop the car. You keep going. Why? Because your dad's trying to make good time behind the wheel. He's driving. It's like, we're going to get there. It's an 8-hour trip. We're going to get there in 7 hours and 48 minutes. We're going to cut 12 minutes. It's like, but my finger's cut off. I'm trying to balance reactions. I'm bleeding all over the back seats. Like, move on. Wrap it up. Just put some dirt on it. We're good to go. We will get there. We're going to save 12 minutes. How about like when you had to go to the bathroom? Did your parents always stop when you had to go? They're no, like, no, we're going to go. You're like, well, we've been in the car for 8 hours. I've got to go. No, we're making good time. We're not going to stop now. Oh, anyway, go ahead and start. We've got 8-6. Sorry, 8-6. Enjoy watching the demos. Balance first, watch second. These are there's one on there that's not one of my all-time favorite reactions. But most of these are going to be stunning display of chemistry. Visual displays a stunning display of chemistry. I can't think of a better thing for the weekend. I'm sure tonight many of you are going to have the urge to want to watch these together. Invite people over. And like, you know how you like to watch, like, has anybody ever binge watched any shows on TV? Where like you start watching Friday night and Sunday night, you're still sitting there binging, watching. These reactions will make you do that too. Like when you start watching these fabulous displays of chemistry, it's like you want to binge every reaction on YouTube. I caution you to not do that. I also caution you to not try a few of these at home. Please, don't do some of these. These are not always safe ones. So enjoy watching. Do not replicate them.